Hi again. In this Lab 3A video, we will be trying our hand at some gear design calculations. In our past lab videos, we have learned about part modeling and creating part drawings in Inventor. And in this video, we are both literally and figuratively switching gears to get some practice with gear train design. So our main focus will be on spur gears, but we will also look at some warm gear examples and some mixed gear trains like the ones shown schematically on this slide. So let's start with spur gears and a little bit of review. Recall that spur gears are used to transmit motion from one shaft to another parallel shaft. We say that two of these gears are mated or meshed together when their gear teeth are engaged, and the resulting set of two gears is called a gear set. The smaller gear is called the pinion, and the larger one is called the gear. We learned that we can represent these gears by their pitch circle diameters in gear design, which saves us from having to draw out all of the teeth. And we learned the relationship between three important gear parameters: this pitch circle diameter D, the module M, and the number of teeth, which we label Z. For example, if we have a gear with 25 teeth and a module of 4 millimeters per tooth, we can calculate its diameter according to the formula D equals MZ, which is 25 times 4, or 100 in this case. In addition to this relationship, another important gear design parameter is the gear ratio between meshing input and output gears, which can be described as a ratio of angular velocities, of diameters, of radii, torque, or the number of teeth for spur gears. These equations will be the foundation of our gear design calculations, but there are a few other practical considerations that we need to keep in mind as well. First, we need to make sure that all of our gears have a whole number of teeth, and that the module between meshing gears is the same. Otherwise, the teeth won't engage properly. So if we specify a module for our gear design calculations, we know that we can only set either the number of teeth or the diameter for our gears, and the other will be automatically set according to the equation D equals M times Z. Since we need to ensure a whole number of teeth, this means that it's often wise to set the module and then the number of teeth, and then to determine the resulting gear diameters according to this formula. And with all of this in mind, let's go ahead and try some examples. In this first warm-up example, we have an input gear with 20 teeth spinning at 100 radians per second clockwise. So CW stands for clockwise here. And we want to know how fast the output pinion is spinning if the output pinion has 10 teeth. To figure this out, we can start by calculating this gear set's gear ratio from the ratio of teeth on the output to the input, which will be 10 over 20, or 1/2. This ratio is also equivalent to the ratio of our input to output speed, so if we rearrange, we can solve for the output speed to get 100 times 2, or 200 radians per second. To finish off this problem, we should also indicate the direction of rotation, so if our gear is turning clockwise, then the pinion must be rotating in the opposite direction of counterclockwise, so we will indicate that in our answer as well. The pinion rotates 200 radians per second counterclockwise. In the second example, we have added another gear with 15 teeth to our gear train, meshed with the 10-tooth gear, and we now want to know how fast this third gear will spin. We already determined that the second gear will be spinning at 200 radians per second counterclockwise, and if we perform the same calculations between the second and third gear, we obtain a gear ratio of 15 over 10, or 1.5. So its output speed would be 200 over 1.5, or about 133 radians per second in the opposite direction, meaning clockwise. Note that we can calculate the overall gear ratio for this gear train by multiplying the gear ratios of meshing gears. This would be Z2 over Z1 times Z3 over Z2, which simplifies to Z3 over Z1. This tells us that the second gear, which is called an idler gear, has no impact on the overall gear ratio. If we changed its number of teeth and diameter, it wouldn't make a difference in the overall gear ratio, and the output speed of the third gear would still be the same. It would, however, change the center distances between gears, which is one of the uses of these idler gears. This slide just highlights the equation for the overall gear ratio that we used in the previous slide, where the output angular velocity is equal to the input velocity divided by the total, or the overall gear ratio. This overall gear ratio is again calculated as the product of individual gear ratios for meshing gears in a gear train, In the previous slide, we calculated these ratios using the number of teeth, and here we see an alternative form using pitch circle diameters instead. In our past example, the 3 gears were all meshed in series, but we could also connect gears in a compound gear train arrangement, as seen in this example, where the 10-tooth and the 30-tooth gears are connected axially, meaning that they must rotate at the same speed in the same direction. If the 20-tooth gear is our input and we want to determine the speed of the output gear, we can again determine the overall gear ratio by multiplying the individual gear ratios for our meshing gears. So for this example, that would be I equals Z2 over Z1 times Z4 over Z3. Note that we don't have a ratio for Z3 over Z2 because these gears are connected axially, they are not meshed. If we plug in our numbers for this example, we get an overall gear ratio of 1/4, and we know that this is equal to the input velocity over the output velocity. So if we rearrange for the output velocity, that gives us 400 radians per second, which is a 4-time speed increase. Finally, the direction of rotation of the output gear will be clockwise, since the 10-tooth gear will rotate counterclockwise, and so will the 30-tooth gear since they are axially connected, and the output must rotate in the opposite direction of that one since they are meshed. So this is one example of a compound gear train, which enables us to achieve higher speed reductions or increases in this case. Here's another more complex compound gear train, and here we are asked to compute the overall gear ratio. Again, we calculate the overall gear ratio by multiplying the ratios of meshing gears. So assuming these values in the diagram correspond to gear teeth, and that our input gear is the 20-tooth gear and the output one is the 10-tooth one, our ratio will be 30 over 20 times 10 over 30 times 10 over 30 times 20 over 10 times 10 over 20. Note that we didn't include a ratio for the axially connected 10 and 30-tooth gears because they aren't meshing. As we saw before, for the gears meshed in series, the intermediate idler gears get canceled out of this equation, leaving us with an overall gear ratio of 10 over 20 times 10 over 30, or 1/6. We can also determine the direction of rotation of the output relative to the input, knowing that an odd number of meshing gears in series will have the output rotating in the same direction as the first gear, and an even number of meshing gears in series would have the output rotating in the opposite direction to the first gear in the series. So here we have 2 sets of gears meshed in series. In the first set, there are 3 gears, so the 10-tooth output of the first set will rotate in the same direction as the first gear, and the first 30-tooth gear in the second set will also rotate in the same direction since they're connected axially. There are 4 gears in the second set, so we can conclude that the output will rotate in the opposite direction as the input. The second part of the question asks if this is a valid design, and this brings up another important consideration aside from gear ratio. One important consideration is the placement of gear axes, because we do need to mount all of these gears on something to get a functioning gear train. In this setup, we see that the center of this 10-tooth gear actually overlaps with the 30-tooth gear in front of it, so its axis would be interfering with the 30-tooth gear. For this reason, this would be an invalid design. So in the last example, we saw that the intermediate meshing gears in the gear train did not have any impact on the overall gear ratio. These gears only serve to change the direction of rotation and also the span of the gear train in terms of the distance between the input and the output gears. If we want to achieve a large gear ratio, meshing gears in series won't help us. Alternatively, the compound arrangement will enable us to achieve higher gear ratios, where we design pairs of meshing gears with the output of one connected axially to the input of the next. This is because the overall gear ratio will be the product of all of the individual gear set ratios, so this is a good strategy to adopt when you're working on gear design calculations. One thing to note on this slide is that we've used the number of teeth rather than diameter to compute the overall gear ratio, and we know that both the ratio of gear teeth and the ratio of gear diameters will give us the gear ratio, so we could use either of these parameters to design our gear train. However, there is one really good reason that we'd want to work with the number of teeth rather than the gear pitch circle diameters in the gear design process. Remember that D and Z are related via the module M. So if we design our gear train using diameters D, we are automatically specifying the number of teeth as well, and we risk having these being fractional values. For example, say you design a gear set where the gear has a diameter of 30 millimeters and the pinion has a diameter of 15 millimeters for a gear ratio of 1/2. If you had also set your module to be 2 millimeters per tooth, then the pinion would have 7.5 teeth, which is not a valid design. For this reason, a strong recommendation for gear train design is to set a module and then go ahead and design the gear train based on the number of teeth, so that you can ensure all of your gears will have a whole number of teeth, and then you can calculate your diameters according to the formula D equals M times Z. So let's consider a design example where we want to make a 6-gear compound gear train as shown in the diagram, and we want the overall gear ratio to be 6, with the input and outputs turning in opposite directions. We know that our overall gear ratio will be equal to Z2 over Z1 times Z4 over Z3 times Z6 over Z5, and we want this to be equal to 6, which we can also write as a fraction 6 over 1. We also have the constraint that the minimum number of teeth on a gear is 10. So looking at our denominator here, where we have a product of 3 gear teeth, we know that this number has to be at least 10 times 10 times 10, or 1,000. Because of this, I'm going to write out the overall gear ratio as 6,000 over 1,000. And I'm going to try to factor the numerator and denominator into 3 whole numbers that multiply to give the overall value. For example, 6,000 could be written as 15 times 20 times 20, and 1,000 could be written as 10 times 10 times 10. This means that we could propose a design with Z1 being equal to 10, Z2 equal to 15, Z3 equal to 10, Z4 equal to 20, Z5 equal to 10, and Z6 equal to 20, since these two ratios are equivalent, and that would be a valid design. This, of course, is just one possibility. I could have initially multiplied the numerator and denominator by 2,000 or some other value higher than 1,000, and I could have generated another design from that. The key idea is that we can write out our overall gear ratio as a ratio of large whole number values, and then we can try to factor it out into whole numbers that will be the number of teeth for our gears. Once we have the number of teeth determined, we can set a module and use this to calculate our gear diameters. Remember, a large module means we'll get a larger coarse tooth gear, and a smaller module will lead to a smaller gear with finer teeth, according to the formula D equals M times Z. So selection of an appropriate module is often important given the spatial constraints for a design. Perhaps the whole gear train has to fit within some frame or some volume of space, so the diameters and therefore the module can't be too large. Another way you can think of this is that a smaller module would give us more precision in adjusting the gear ratio. For example, if we had a gear set with pinion and gear diameters of 10 and 20 millimeters, a 1 millimeter module would give us 10 and 20 teeth. If we increase the number of teeth on the gear to 21, which is the smallest increase that we could possibly do, since the number of teeth has to be a whole number, this would change the gear ratio to 2.1, an increase of 0.1. On the other hand, if we had a module of 0.5 millimeters, then our pinion and gear would have 20 and 40 teeth, respectively. In this case, a 1-tooth increase for the gear would result in a new gear ratio of 2.05, half of what we achieved with the module of 1 millimeter, which demonstrates that a smaller module enables finer gear ratio adjustment. So you might be thinking, well, why don't I just make the module really, really small? Then I could have a great deal of precision in setting gear ratios. The problem with this is that a smaller module leads to finer teeth, and we can see an extreme of this in the picture to the right, where the teeth are so small that our gear basically just looks like a circle. So you can imagine that a gear set with too small of a module, and therefore too small of teeth, will probably have poor tooth engagement and will be prone to gear slip or disengagement. So the moral of the story is that a smaller module will enable greater design precision when gear size is constrained for compact packaging, but we have to find a good balance where the module won't be too small for our gears to function. For example, if we considered our previous 6-gear design, where our gear teeth ranged from 10 to 20, but now we introduce the constraint that the entire gear train must fit within an 80 by 70 millimeter space, we might select a module of 1 millimeter in this case, which would give us gear diameters ranging from 10 to 20 millimeters. Then the distance from the leftmost edge of our first gear to the axis of the second gear would be 17.5 millimeters, and the distance from that same axis to the rightmost edge of our fourth gear would be 25 millimeters, giving a total span of 42.5 millimeters for our gear train, which is well within the 80 millimeter constraint. Say we select a gear face width of 5 millimeters and a spacing of 10 millimeters between gear sets, then that would also be well within the 70 millimeter constraint. So these are some of the considerations that you'll have to make in gear train design. Now let's move to another type of gear, the worm and worm gear. Recall that the worm is like a screw that drives a worm gear with the input and output drive axes perpendicular to each other. The greatest feature of the worm drive is that it is capable of very high speed reductions, where the gear ratio is calculated by the number of teeth on the worm gear divided by the number of threads on the worm. For example, if we had a 1-thread worm spinning at 100 RPM meshed with a 20-tooth worm gear, we can calculate the worm gear speed as the worm speed times the number of threads on the worm divided by the number of teeth on the worm gear, which gives 100 times 1 over 20, or 5 RPM, which is a 20 times speed reduction. We can combine worm drives with our previous spur gear trains to obtain mixed gear trains, and the gear ratio calculations are the same. We just multiply the gear ratios of meshing gears. So in this example, our overall gear ratio would be 20 over 1 times 20 over 10 times 10 over 20 times 10 over 20, which simplifies to 10. We know that this gear ratio is equal to the input speed over the output speed, so rearranging this gives an output speed of 100 over 10, or 10 RPM. And we can determine from the diagram that the output gear will spin counterclockwise in the opposite direction of the worm gear. And this is using all of the same calculation strategies that we saw before. If we add another gear set before the worm drive and leave everything else the same, we can update our overall gear ratio to include this new gear set as well. So our new overall gear ratio will now be 10 times the additional gear set ratio of 10 over 15, which gives us 100 over 15. We can calculate the output speed using the same formula of our input 100 RPM divided by the gear ratio of 100 over 15, and that gives us a new output speed of 15 RPM. So we've now covered spur gear train design and worm drive design, as well as gear calculations for mixed gear trains. These examples focus mainly on the mechanics of gear design calculations. However, there are other important things to consider in the design process before even getting to the calculation stage. Determining the appropriate gear type is one important consideration. We focused on spur gears and worm drives, but remember that other gear types exist like helical and bevel gears that are more appropriate for some applications. Another related consideration is gear configuration, which involves determining the number and the arrangement of gears that you think is suitable for the design problem. Generally, a smaller number of gears is better because simplicity is always good, and a more complex gear train with many gears is more likely to break. And then once we settle on a gear type and configuration, we can go ahead with gear calculations to determine appropriate gear parameters. And we might find, once we reach step 3, that our proposed design doesn't work the way we wanted, or we might think of another arrangement that could be better. So it's important to understand that these design steps are iterative and not necessarily linear. You'll get experience with this design process in your project. But this wraps up this video on gear train design calculations, where we focused on spur gears, worm drives, and mixed gear trains. In Lab 3B, we will take our gear design to Autodesk Inventor and learn how to use the Design Accelerator to model spur gears.